All right, welcome back. I hope everyone had a good lunch. Today, we're going to start our afternoon off right, and that is with some math. We're going to be having some fun with functions, and I'm going to be showing how to find custom fast math approximations using popular Python packages. I want to thank ADCX for having me. My name is Ryan Robinson, and I'm an independent developer from Southern Oregon. And I think my background is maybe a little bit non-standard. I did spend 5 years teaching high school math before I got into software. And I don't know if you've ever tried to teach math to high school students. They're not the most receptive crowd. So I'm certainly excited to be talking to some people that will maybe be a little more interested in the topic today. I work on mainly iOS and Android apps, and I've been fortunate that one of my apps, AutoPad, has done pretty well. It's found a good following in the church music community. So I'm super excited to be here. What I'm going to be talking about is showing how to use popular Python packages to find custom fast math approximations. I'll have time to do just a little bit of high-level theory. I'll show some Python code examples, and we'll do a little bit of kind of compare and contrast evaluation and benchmarks and such. So first, we might want to ask ourselves, why would we even want to do this? We know that the use of these special math functions is extremely common in audio. For example, if you have an oscillator, you'd be calling some kind of periodic function, like sine or cosine. Nonlinear processing, we're using a lot of hyperbolic tangent. We do unit conversions. Pretty much any kind of special math function that you learned about in high school, we're using it, and we're using it quite a bit. And these things aren't necessarily cheap to compute. The standard library will have to be pretty robust. You need to be able to handle any kind of input. And obviously, you want full precision from some kind of standard implementation. In audio, though, we might not need all of those features that the standard library provides. Our inputs are quite often in a known range. For example, if you have an oscillator, your phase would be maybe between 0 and 2 pi. We may not need full precision. We're also under pretty tight time constraints. Anything we can do to speed up our code, we're generally happy to do. And we also might want to vectorize things. There's a lot of opportunities for parallel processing. So if something is pure arithmetic, we can use SIMD instructions pretty easily for those things. So what we will be doing to develop a fast math approximation is finding a polynomial or rational function that approximates the kind of special function that we want to know on some kind of defined range of inputs. And obviously, this huge subject area, and I'm only going to be able to scratch the surface today, but I'm going to show Taylor polynomials, Pade approximants, and minimax approximations. And then we'll just spend a little bit of time kind of seeing how we did, comparing and contrasting these three methods. So first up is Taylor polynomials. And if you took calculus, you know that you're trying to find a polynomial whose derivatives match the corresponding derivatives of your target function at your central point. That would be given by this expression here. We know that a polynomial is just a sum of powers of x. And in this case, our coefficients are just the sort of values of the successive derivatives at that point A. And we're just kind of dividing by that factorial and factorial because we have the successive applications of the derivative. These series go on forever, and we're just going to kind of terminate it when we get the desired precision. So here's the first 4 terms of the Taylor series for sine of x, just to kind of see. And if we just show this graphically really quickly, thinking about building up an approximation for sine, starting at the point 0, we can start by approximating the slope of our function, and that would give us our first term, x. And as we kind of match higher order derivatives, we can see that our approximation is going to be tracking with the true sine function for longer and longer. And as we add more terms, things get better and better generally. So to do this in Python, I am using a package called SymPy, which is a symbolic math library for Python. And it knows all of those rules from calculus, and it will just kind of do it for you. And so what I've defined here is just a simple function called getTaylor, where I can pass it an expression, a variable, a central point, and a degree. And then what we're just going to do is call series on our expression. And then we kind of have to do a little bit of housekeeping. It kind of bundles up the higher order terms of the series, and we remove those. And then we expand our polynomial. And then there's a bit of finessing to kind of get the floats out. But then we just return, in this case, I'm returning this NumPy polynomial. And we can use it like this. And I just want to give a little bit of a disclaimer. You know, these are kind of examples meant to be kind of showing the pros and cons of each method. I wouldn't necessarily recommend just using this kind of 9th degree Taylor polynomial. You certainly want to think about the pros and cons of each of these methods, and we'll get into that as we kind of go on. But this is how we would kind of use that code right there. I think a couple interesting things before I go on is that the SymPy library, it actually kind of interprets things as symbols. So we're actually just passing sign of x, kind of how we would write it on paper, which is a little bit different from the other libraries, such as NumPy, that we'll be using. So these are the coefficients we get. Now, I mean, not too much to say, except that it should be fairly easy to take these things and put them into a C or C++ function. One thing we'll note is that we do actually have a bunch of zeros, and those come from the symmetry of the sine function. We saw that the Taylor series only has odd powers of x. So that's actually pretty nice. Will save us, we can essentially skip those terms when we go to compute this. And if we look at our error curve, it's fairly consistent with what we kind of expect from the theory, where we stay, and I'm looking at relative error, by the way. We stay very close to the true value, and near the edge of our input range, we kind of steer off course rather quickly and rather abruptly. So that's something we'll be looking to improve on with these other methods. So just a quick summary, I would say the pros of using a Taylor series or Taylor polynomial is that we only have multiplies and adds, and we get some benefits from symmetry in the case of functions like sine. But we do not have consistent error along the entire input range. And also polynomials in general, their end behavior isn't great for this because as you plug in larger and larger values of x, they tend to explode to infinity. So it would be nice if we could come up with some solution that doesn't kind of dramatically explode to infinity. And we'll see how to address that with actually the next topic, which is Pade approximants. And Pade approximants, you start by actually taking a Taylor polynomial and setting it equal to a rational function. And that's what we have here. The coefficients in the Taylor polynomial, these would be known values. And in this case, these a's and the b's would be what we're looking for. And it's actually fairly easy. It's just a lot of kind of tedious algebra. We move this denominator up and we multiply everything out, and then we end up with kind of a huge linear system where we can kind of match up our coefficients of corresponding terms. To just show this graphically, this is another example with sine of x. We have a polynomial for our numerator and a polynomial for our denominator. And taking those as a rational function, we get some pretty nice tracking for this example in a fairly narrow range. But I want to compare it with the Taylor series. And the thing to note here is that when we take a look at the kind of corresponding Taylor series, when the Taylor series does pull away from the sine function, it pulls away much more quickly, and it kind of shoots to infinity at a much faster rate. And that's because rational functions, they just have nicer end behavior. They're not going to be exploding to infinity as fast. So to do this in Python, we use SymPy for the Taylor series. We're going to use SciPy for a Pade approximant. And SciPy actually just provides a Pade function that we can just use. We do have to be careful to pass our coefficients in the correct order. And then we just tell it the degree of the denominator polynomial that we want. So here's an example of me using it. I get my Taylor series, and then I just pass those coefficients in. I'm asking for a 4th degree polynomial in the denominator, and then the numerator just sort of adds to make 9 in this case. So we'll have a 5/4 degree Pade approximant. And if we look at the coefficients, again, not much to say. We would take these, put these in some kind of C or C++ function. And we still have those zeros, which is pretty nice, which means we're still getting those benefits in the case of sine, of like the symmetry of the function. So that's pretty good. And if we look at our error curves, it's pretty consistent with what we would expect from the theory. The Pade approximant is able to hold more closely to the true value for a little bit longer. And when it does diverge, it kind of diverges less dramatically. So I would say that is definitely an improvement. We have better end behavior because we're using a rational function, and we're holding more closely to the true value for longer. However, we still don't have a consistent error along the entire input range, which we'll kind of address with the next method. And this does require division, so it's not quite as snappy as maybe just pure multiplies and adds. But I think the division is probably worth the trade-off, or worth it in this case, and that's certainly what the Juice developers felt. They have a great little header that's the fast math approximations, and all of their fast math approximations actually use Pade approximants. So you're not going wrong if you're doing it the way Juice does. And just for comparison, their Pade approximant for sine is degree 7 over degree 6. So just to kind of give you an idea of where my examples kind of fit in terms of the things that would actually be used in production. So to finally address the issue of kind of the uneven error or inconsistent error along the input range, we're going to turn to this method called minimax approximation, which what we're trying to do here is find a polynomial that is minimizing the maximum value of some error function along our input range. And what this does is it kind of takes all the error and forces it down into this oscillating curve where we're moving up and down between a high and low value. And there's an iterative take a step back. There's an iterative algorithm for doing this known as the Remez algorithm, but I'm actually going to use kind of a general purpose optimization package for this in Python. We'll say a little bit about error. First off, the benefit of the minimax method is that you're always going to know kind of the worst case outcome for your approximation. That's what we get by minimizing the maximum value of our error function. And then we'll kind of just think about the error function we might want to use. In this case, and from my reading, I think the way to go is relative error. What that effectively does is it normalizes our error, and it makes it easy to kind of guarantee how many bits of precision we're going to be getting out of our approximation. If you take two normalized floats where you have the same exponent on the twos, it's really easy to just look at them, see where the bits differ, and then you can say, okay, I'm always going to have at least 10 bits of precision with this approximation. So to do this in Python, I'm using a package called CVXPy. It's kind of a general purpose convex optimization package, and it's certainly up to the task. It gives us freedom to choose our error function and set our constraints. So I'm going to just do a little bit of housekeeping at first in this function. We're passing in a function that we want to approximate, the degree of the polynomial that we want out, and the low and the high end of our range. And then we're just going to create an array of input values for our function, and then we're going to compute the true y values. Since we're going to be dividing by y to compute relative error, we're going to remove y values close to 0 and hope for the best. Here's the actual CVXPy code. This is just a continuation of that same function. I create a vector of coefficients for my polynomial. This is a CVXPy variable. And then I'm going to go ahead and compute a big matrix, which is the kind of x part of my polynomial. For every input value, I need to know x to the 0 power, x to the first power, x squared, and so on. And then I just create my objective, which is the quantity that I'm going to be asking CVXPy to minimize. We do some matrix multiplication. We subtract our true y values and divide by the y values. And then taking absolute and max kind of reduces all of this to a single number, which is our maximum relative error along the entire input range. One thing that's kind of fun about CVXPy, that's kind of nice, is that we can add constraints. So if our function has special values that we want to try and preserve in our approximation, we can add those, and the solver will do its best to kind of accommodate us there. Then it's just a matter of defining our problem and giving it that objective and the constraints. And then we just call solve. And we're going to return these coefficients. The vector A now holds the optimum coefficients for our approximation. So doing this with a 7th degree minimax approximation, these are the coefficients we get out. The only thing to really note here is that now we're not getting those zeros that come from the symmetry of the sine function. And that's because we're kind of using those extra coefficients to help kind of normalize our error along the input range. So I think, before pros and cons. If we look now at our error curve, we can see that we have this characteristic error curve where we're oscillating up and down between a high and a low value. So it's pretty nice. The error is controlled within the input range that we want. So I would say there's a lot of benefits to using the minimax method. It's fairly customizable. Your error, like I said, stays within well-defined bounds along the entire input range. And any of the sort of end behavior issues that come from using a polynomial are pushed outside of that. We can't take advantage of symmetry, and working with a solver, it can be a little finicky. The numerical methods, you kind of have to work with it to get it to give you what you want sometimes. If we now compare the relative error of all three, we can see that our minimax approximation stays pretty close to 0 throughout the entire input range, so that's pretty nice. Looking at the bits of precision we get out of our functions, and I'm just using these kind of simple calculations here. Our Taylor polynomial and Pade approximant do kind of suffer at the edge of the range. In the worst case, the Taylor polynomial doesn't even give one bit of precision. But the minimax approximation of degree 7 is, in the worst case scenario, able to give us 10 good bits, averaging 11. And if we take a look at absolute error, it just gives us a little bit more of the picture. We can see that the minimax error is oscillating up and down. Looks like I got to wrap it up. Let's just do a benchmark. This is just throwing these things into C++ functions and going to QuickBench. And we can see that we do get some nice improvements over standard sine. And I will just say these are all pure arithmetic, so it should be fairly easy to use SIMD instructions with these functions if we want to do that. And so just to wrap up, I know that was kind of a lot. We've even just amazingly barely scratched the surface. I showed Python examples for generating custom fast math approximations. I do have this code on GitHub, which I think is hopefully available on the Zoom event page. And we discussed pros and cons and compared error curves. And I would just encourage people to kind of mess around with this stuff, have fun tinkering, and maybe you can pull this in to your code and speed up some of your calculations. Thank you.
Are you familiar with ConstExpr and possible ways of, say, computing your coefficients at compile time for your functions?
Yeah, I have not tried to do this personally, ConstExpr, but I have messed around with ConstExpr and doing some kind of filter coefficients. So it certainly seems possible. I have not explored that personally.
Oh, just real quick, do you find that adding constraints, especially since it is sine function, at pi over 2 and stuff like that,
yeah,
greatly affects the error, or does it tend to be somewhat minimal effect?
Every constraint you add, you kind of lose, I guess you could say, a degree of freedom in terms of you have to use that in the coefficients to accommodate that. So I wouldn't say it's dramatic, but certainly you can't go to town with adding constraints, right? So there's certainly a balance, and there's pros and cons to be weighed with all the methods.
Very quickly, did you look at rational Remez exchange approximation, rational Chebyshev approximation?
You know, I looked at that. I couldn't get it into the talk, but I think it would be reasonably easy to kind of modify the CVX pi example to do that. I haven't done it yet. I couldn't get into the talk.